Hi again, everyone. So welcome back. Let me start by saying that at this point in linear algebra, we have established a lot of the objects that we will be looking at in the course. Some of the objects that we use in linear algebra are matrices, vectors, systems of equations, scalars, things like that. Um, in this section, we are going to introduce another important type of object called a linear transformation. And this section is called Intro to Linear Transformations because we're going to have multiple sections to talk about them. But let's at least get started and see what they're all about. So, Intro to Linear Transformations. Before I can tell you what a linear transformation is, we're going to start with the definition where I'm going to tell you what a transformation is, and we'll worry about the linear part later. A transformation in parentheses, I'm going to say sometimes we might refer to it as a function or as a mapping. So a transformation, or a function, or mapping, t, from Rn to Rm is a rule that assigns to each vector x in Rn a vector t of x in Rm, period. So this should look familiar to you in regard to functions, right? You've talked about functions in classes before. You know a function is kind of a rule from one set to another. And very often, a lot of the functions that we talk about in math classes, in algebra and pre-calculus and calculus, a lot of functions that we talk about assume that the inputs are going to be real numbers and the outputs are also usually going to be real numbers. What makes this a little different is that now we are going to say that the inputs are vectors and the outputs are also vectors. And they might not be the same size. We have vectors with n entries, vectors in m entries. Now, I wrote definitions, plural, so there's going to be a couple of extra definitions here. When we talk about functions in math classes, what's one of the first things that we usually talk about? Or what are two of the things that we usually talk about right away? It's going to be domain and range. But let's be careful here. It might not be domain and range. It might be domain and something else. So the set Rn, that's the set that we are taking objects from. This is called the domain of T. Let's be careful about this next one. The set Rm is called okay, let's be careful. Is Rm the range? Or is there another word for it? You may have seen in an algebra class at some point. Well, the answer is it might be the range or it might not. The domain is the set of all possible inputs. The range is supposed to be the set of all possible outputs. But if we have a transformation t from Rn to Rm, we don't necessarily know if all of Rm is possible to reach as an output. So we have a different name for it. We call it the codomain. And I think that it is fair to say that the range is a subset of the codomain. We'll talk about that a little more in a minute. I'm going to say note, what if n equals 1 and m equals 1? then t is a function from R to R, right? And in that case, that's the sort of function that we've always worked with in math classes, calculus, etc. But now our definition is more general to include the traditional types of functions that we're used to as just being one special case. But it's more general because now we are able to work with vectors. We may use the notation T colon Rn arrow pointing right Rm. So that notation tells us that there is a transformation from Rn to Rm. It's just like what I wrote above. I'm going to point to it up here. T from Rn to Rm. It's the same thing, except we use some symbols instead of words. The colon basically means from in this context, and the arrow pointing to the right means we go from Rn to Rm. Tells us which is the inputs and which is the outputs, which is the domain, which is the codomain. Now, a couple of notes. If we're given x in Rn, the vector t of x in Rm is called the image. I'm going to underline that. The image of x. And in parentheses, I'm going to put something here. It's the image of x under the action of t. So that's the kind of full phrase. But a lot of times we would just call it the image of x and leave out the part that I said in parentheses. It's usually okay to do that because it's usually clear from context that we're talking about a transformation t. If I say t of x and say, oh, that's the image of x, we understand that the action that took place was t. So you have an input and an output. The output is called the image of the input vector. And finally, the set of all images t of x, so all possible images, is called the range of t. And in some cases that might be the codomain, in some cases it might not. In fact, if you think about it, in a class that you had on learning how to write proofs, you probably learned a word for that. Like, what if the codomain and range are equal? There's a word for that. We're going to get to that soon. Okay, I don't want to get too far ahead of myself. Transformation maps from Rn, and we're going to use this notation a lot. T goes from Rn to Rm. So let's look at some examples of transformations, okay? Now, I haven't necessarily told you what a linear transformation is yet. I just want to do some examples of transformations. Example 1 is going to be the transformation from R2 to R2, defined by... Transformation is supposed to be a rule for assigning a vector to another vector. So we could have a formula that explains how the rule works. And I'm going to say that it's defined by the formula t of the input vector equals this. So for every vector that you put in, x, y, the output is the vector yx. That's an example of a transformation. For example, t of 5, 1 equals 1, 5. And t of negative 2, 3 equals 3, -2. So this is a transformation that takes x and y and swaps them. Because this transformation is taking place in R2, and because the coordinates are x and y, we could maybe try to visualize this as points on the xy plane. So let's visualize this one. We're not going to be able to draw all the transformations we look at today. Let's look at this one, though. So we could have an x-axis, a y-axis. Let's see if we could figure out, what does it look like? I'm not trying to graph this entire function. That's not what this picture is about. I basically just want to take these example points and see if we can visualize what's happening. So, for example, this first one, if we say that input vector 5, 1 could be thought of as corresponding to the point 5, 1. So that was an input. What happened to it when we sent it through this transformation? It went from being at 5, 1 to being at 1, 5. So t, I'm drawing both of them on the same picture. T did this. T took our point and sent it over there. Okay, so here's 5, 1, and here's 1, 5. What happened to the other point? If I start with -2, 3, that's up here, -2, 3. Where does that get sent when I apply the transformation t? It gets sent to 3, -2, so it gets sent over here. 3, -2. So this is happening. I'm drawing an arrow to kind of indicate direction. Like, you can tell, because I drew arrows, you can tell which one is the input and which one is the output. You have kind of an origin and a destination, starting point and end point. So you could try other points. Let's make some observations about this. Some observations. I want to say that what this transformation does is it reflects points across the line y equals x. Can you see that that's what's happening? If I were to draw the line y equals x, graph the line y equals x, you know what that would look like. Basically, any point that I put in as an input, we're getting the mirror image of it, where the line y equals x is the mirror. So that's one observation. You could say that's what this transformation is doing. Another observation is that t of the origin equals itself. I used the word origin because we're thinking of this visually, but another word for that would be the zero vector. T of the zero vector equals itself. What are some other things that you might notice about this? One thing I notice is, what if I did t twice, like t of xy? Apply the transformation, and then apply it again. Gets you right back where you started, xy. Because it's like taking 5, 1, you'd send it to 1, 5, then you'd send it back to 5, 1. And you might look at this and say, like, that's an interesting property. It seems like some transformations would do that, but it seems like most transformations probably would not do that. Another observation is that in this case, the range is all of R2. I think we could get to any point in R2 by putting in the appropriate input. So everything here, this wasn't really like an example problem. This was just an example of a transformation. We talked about it a little bit. And I have a couple of other transformations I want to show you as well. And that's probably the only one that we're going to draw a picture. That was example 1 of a transformation. Let's talk about example 2. This is going to be t from R3 to R2, defined by, very often a transformation is going to be defined by a formula, just like ordinary functions are often defined by formulas. There might be other ways to define one, but for now, this is a good way for us to establish what we're talking about. So I need my input vector to have 3 entries, right? We could call it XYZ, or we could call it X1, X2, X3, whatever you want. Because it goes from R3, but it goes to R2. So the example that I want to give you is I need to do a vector in R2 here, and it's going to be X1. Let's see if I can fit this here. X2 plus X3. Let me zoom in for a second. Can you see that? T sends X1, X2, X3, sends it to the image would be X1, and then down here is X2 plus X3. So this is another example of a transformation. For example, what if I did t of 1, 2, 3? What would the image of 1, 2, 3 be? Well, the image would be 1, 5. See where I got the 5 from? It's from 2 plus 3. Okay, so the point of this example was just to show you that transformation could go from one sized space to another sized space. So like R3 to R2, they don't have to be the same. Example 3 of a transformation. T maps from R2 to R, defined by T of, we need 2 inputs, so let's go X1, X2. So what's the output here? A real number? I could call it a vector that only has 1 entry. That's how I'm going to choose to write it for now. I'm going to write it as a vector with 1 entry, and it's going to be X1 times X2. So this is a transformation that it expects a vector in R2 as the input, and the output is the 2 numbers multiplied times each other. For example, t of 2 comma, I almost wrote it as comma, but t of 2, 3 equals 6. So you multiply them together. All right, so we've seen 3 examples of transformations, and I think what I've got planned is going to have us talk about these examples a little bit more in a few minutes. We're going to revisit each of these. But now that we've seen definitions like transformation and image and domain. Now I can tell you the definition for linear transformation. So definition: a transformation T is a linear transformation if there are some requirements. Okay, there are some requirements, and not every transformation is going to satisfy these requirements. We're going to write this as having two requirements. Condition 1, T of u plus v must equal T of u plus T of v for all vectors u and v in the domain of T. Okay? And there's one other requirement. A linear transformation has to satisfy that. And also, T of Cu, where C looks like it's a scalar, U looks like it's a vector, has to equal CTU. For all scalars C and all U in the domain of T. If both of those conditions are satisfied, then the transformation is called a linear transformation. Okay, and this is going to be an important definition for us. Linear transformations are going to, well, let me put it this way. Linear transformations are going to be the most important transformations for this course. You know, we talked about some transformations above. Maybe some of those are linear, maybe some of those are not. We're going to look into that. But in general, linear transformations are the ones that are important for linear algebra. Now, why are they important? There's a key idea behind these two conditions. The key idea is that linear transformations, they map vectors to vectors, but in particular, linear transformations preserve the operations of vector addition and scalar multiplication. Let's think about this. Why am I using the word preserve? Maybe I can say this in another way. So in other words, condition 1 here, condition 1 is saying, you know that usually you do what's in the parentheses first because of order of operations. So if you look at the left-hand side of condition 1, condition 1 says you can add two vectors and then do T. Or you can do T first and then add the vectors. And either way, you get the same result. We put an equal sign between them. You can add two vectors and then apply T, or you can apply T to each of them and then add. You get the same result. We say that that's preserving the operation of vector addition across the transformation. And then over here, you can multiply a vector by a scalar and then apply T, or you can apply T and then multiply by the scalar. The scalar multiplication can be done before or after, and either way, they equal each other. You get the same result. Those two properties have to be satisfied for a transformation to be linear. There are some other properties that follow from these. If these two are true, if a transformation is linear, then there are some other things that we can say about it. So let's say some of them. We're going to call this property 3. And it says that for a linear transformation, I'm leaving out some words here, but this is going to be a property for a linear transformation. It's like we're continuing this list, except these are going to be properties that we can prove. The first one is t of the 0 vector has to equal the 0 vector. All right, and I'll show you a short little proof of this. By property 2 above, like we're assuming that we have a linear transformation, so that means conditions properties 1 and 2 are satisfied. T of the 0 vector is equal to t of 0 times u, which equals 0 times t of u, which equals 0 vector. End of the proof. It's a one-line proof. Maybe I wrote that pretty quickly, but take a look at this. If you have a linear transformation, then you know property 2 is satisfied. If you know property 2 is satisfied, t of the 0 vector could be rewritten as t of 0 times a vector. Property 2 says you can pull the 0 out front. 0 times a vector is the 0 vector. So if property 2 is satisfied, then you also get property 3 for free. This quick little proof that we did, the point of this is that even though there are two properties that make up the definition of linear transformation, there are going to be other properties that kind of follow as a result. And we can put them all together and say linear transformations have a bunch of properties, not just the two requirements. I'll show you another that we're going to call property 4. It's property of a linear transformation. Property 4. So right now, we could use properties 1, 2, and 3 to prove this if we wanted. This is going to say t of cu plus dv equals ct of u plus dt of v, and that this is true for all u and v in the domain of t and all scalars c and d. In a way, it feels like this property looks like it's combining property 1 and 2, doesn't it? Into kind of one statement. So if we know that a transformation is a linear transformation, we're going to say that it must have this property. I'd like you to try proving this. See if you can use property 1 and 2 to prove property 4. So maybe pause the video and take a minute to try this. Okay, here's my proof. I'm going to start with the left-hand side. I want to show that it equals the right-hand side. First of all, this transformation is assumed to be linear, so we could apply property 1, because there's a plus sign in the middle of that. So let's apply property 1 and say that this can be split up into this by property 1. Is that what we wanted? Almost. That's almost what we wanted. So let's do one more line and apply property 2 to pull out the constants or scalars by property 2. End of proof. We started the left-hand side. We applied property 1 and then 2, and we got the right-hand side. So linear transformations have some useful properties. You look at some of these and you say, you know, it's nice to be able to pull constants out. It's nice to be able to split up things that have a plus sign in between them. Let me go back and just show you something here. You've seen a lot of different operations in math that have these kinds of properties, haven't you? Like, you want to add two things that says you could split it up. I'll tell you one thing that you've seen in math where you can do this is derivatives. Derivative of two things, you know, you can split them up with a plus sign in the middle. Derivatives also have the second property, right? You can pull a constant out of a derivative. If this t was like a ddx, I'm kind of getting off on a tangent here, but you know, if you have ddx of something and there's a constant, you can pull constants out of a derivative, right? How about limits? When you have a limit of something plus something, you can split it up into the limit of the first part plus the limit of the second part. What if you have a limit with a constant inside? You can pull a constant out of a limit. You can pull a constant out of an integral sign. So you've seen things in math that have similar properties to this. Maybe not this one. Maybe this one's a surprise. Property 3 that says that transformation applied to 0 is 0. So anyway, 4 properties. Now we have an interesting fact. If a transformation satisfies property 4, then it is linear. I don't know if that seems surprising to you or not. I mean, the definition for being a linear transformation, we said that it has to satisfy property 1 and 2. What I'm saying now is that if a transformation satisfies property 4, then it automatically must satisfy 1 and 2. Therefore, it is linear. And that would make this a nice little shortcut. Like, here's the idea. We're going to have some problems coming up where we're going to be given a transformation, and the question is going to be, here's a transformation, is it linear or not? Is it linear or not? And you could check by checking for property 1 and 2. But this fact is saying, instead of checking for property 1 and 2, you could just check for property 4. Property 4 is kind of like merging properties 1 and 2 into one statement. So, I would like us to prove this fact. Now, I'm going to ask you to try this, but I think what I'm going to do is I'm going to start this. So proof, let T be a transformation satisfying property 4. Okay? I'll do a little bit more of this. I'm going to put in a sentence here. We want to show T satisfies property 1 and 2. Okay? That sentence is optional. I just thought I would throw that in there. That's what we're trying to do. First, we'll show property 4 implies property 1. I guess it feels like I'm being very verbose here. If you prefer to write proofs that are more compact, then by all means, that's okay. We have, let's start with the left-hand side of the property that we're trying to show. We're trying to show property 1, start with the left-hand side of it. Is there a way that we could use property 4 to get this left-hand side to equal the right-hand side? I can't use property 1. I can't use property 1 to prove property 1, right? But I could use property 4. How about this? T of u plus v is the same as T of 1u plus 1v. That's fair, right? Now, I can apply property 4 to this. Property 4 applied to this gets me 1t of u plus 1t of v. And 1 times a vector is just the vector. So this is t of u plus t of v. So that was kind of a clever little trick we did there, where I put 1s in, just to have scalars there to make it look like property 4, and then I applied property 4. Ultimately, we showed that the left-hand side of property 1 equals the right-hand side of property 1. That's what we wanted. Next, we'll show that property 4 implies property 2. So this is the part I'd like you to try. Maybe pause the video here and spend a minute or two trying this. All right, were you able to show it? Let's see. Let's start with the left-hand side of property 2. We want to show that this equals the right-hand side of property 2. And what tricks do we have at our disposal? We have property 4. That's the main thing. I guess you could say technically we could use property 1. Because if I wanted to somehow use property 1, we've already shown property 1 is satisfied. But I'm not planning to do that. I'm planning to just use property 4. So I would like to somehow make this look like the left-hand side of property 4. Property 4, let's just take a quick glance at it. It's up here. T of cu plus dv equals this stuff. So the left-hand side of property 4 has not just a T of cu, it has a T of cu plus this other stuff. How do I make T of cu look like T of cu plus dv? Well, I could call it cu plus 0v. That seems okay, right? And then by property 4, this is C of TU plus 0 T of V. 0 times T of V is 0, so I get C of TU. So that was a cool little trick. And we got what we wanted. There are also other ways to do this, but I'm just going to say, so T satisfies. Let's remember the point of this. T satisfies both requirements to be linear. End of proof. We started by assuming property 4, and we conclude that the transformation is a linear transformation. So if I gave you a transformation and I said, is it linear? You have two options at this point. First option, you could check to see if it satisfies property 1 and 2. Or another option, just check for property 4. Which one is going to be more work? They're probably going to be about the same amount of work, to be honest. So it might just be a matter of preference. As I did this last part of the proof, I said something about how there might be other ways to do it as well. I want to show you one other idea, just in case anyone came up with this when I asked you to try it. Another way to do this is you could say T of CU equals T of half of CU plus half of CU. I don't know if anyone thought of it this way, but it's like taking CU and you take half of it plus the other half of it. That's a pretty cool idea, because then you could apply property 4 here and get 1/2 C T of U plus 1/2 C T of U. What if you pull a C out? We're just, yeah, let's just pull C out. C of 1/2 T of U plus 1/2 of T of U. And then you wind up with CT of U. So that's pretty cool. That's another way you could do it. I used as my, what do you want to call it, weights? Do you want to call them weights? Do you want to call them coefficients? Whatever you, maybe just call them scalars. As my scalars, I used C and 0. But here I'm saying that you could use 1/2 of C, 1/2 of C. Guess you could also use like 1/4 of C and 3/4 of C. So there are lots of ways to prove this. So what I would like to do next, I kind of hinted at this, that this was coming up, is I would like to revisit our 3 example transformations from earlier and check to see if they are linear or not. Okay? We had an example 1, example 2, example 3. So now we're going to revisit all of them. I'm going to do this first one. Is T from example 1 linear? I'll remind you of what this transformation was. It was T from R2 to R2, and it was defined by T of xy equals yx. Okay? Maybe that's kind of an interesting transformation. It swaps x and y. So I'm going to check to see whether or not this is linear. We know it's a transformation. Is it a linear transformation? How about this? We will check for property 4. If property 4 is satisfied, then it's linear. What I'm going to do is let U and V be elements of R2 such that U is made up of U1, U2, and V is made up of V1, V2, because I think I'm probably going to need to refer to those individual entries. And let C and D be elements of R. You should start this type of proof in this way. I mean, this is really a proof. What we're doing is we are proving that it's linear, or we are proving that it's not linear. We don't really know which one yet. But either way, we're showing justification, and we're doing, if we're going to use U, basically, I want to spell this all out so that when we get to the middle of the problem, nobody can sort of question, like, wait a second, what is U1? You didn't say what U1 is. I did say what U1 is. U1 is the first entry of U. See what I mean? So that it's clear to the reader. All right, because we're trying to teach good proofwriting habits and just good problem-solving habits. So we have, let's start with, I said we were going to check property 4. Let's start with the left-hand side of it. Left-hand side of property 4. And we're going to check to see, does it equal the right-hand side of property 4? Remember, I'm not going to assume any of properties 1, 2, 3, or 4. Because if I assume those, then that's like me assuming that this thing is linear. I don't know if those properties are true or not. Let's just work with what we do know. We know that U is this, and V is this. That seems fair. Nothing wrong with that. I also know that I could work with what's inside here. I could call this CU1, CU2, plus DV1, DV2. Let's keep going with this. So why might I do that? I'm doing that because now I have a vector plus a vector, and I can combine them into one vector. I could say this is T of CU1 plus DV1. That's my first entry. CU2 plus DV2. That's a vector in R2. At this point, I just want to say as a quick side note, we're in the middle of this right now, and I want to take a step back and let's remember, what are we trying to do here? We're checking for property 4. We started with the left-hand side of property 4. We're doing a chain of equal signs. This equals that, equals that, equals that. We want to eventually wind up, hopefully, we want to check to see if it equals the right-hand side of property 4. So you could like move up in your notes and look at property 4, look at the right-hand side. I'm hoping that that's what I get to. Or if I get to something else that clearly shows me that it doesn't equal property 4, then that would be good to know also. What can I do here? What haven't we used yet? There's actually something really big that we haven't used yet. See if you can think of it. This thing right here. We know what the transformation is. The transformation switches the first entry and the second entry. Now is the time to do that. So T of that vector equals this vector. That's really big, and we didn't use it until now. Notice that right now, in the last thing that I wrote, there's no T in front of it. Why is there no T in front of it? Because that was me applying T. We applied the transformation T. This is the output that we got. Does this equal the right-hand side of property 4? Well, maybe. Doesn't look like it in this form, but we could work with this. We could manipulate this. We have a vector. Let's start changing it around. One thing we could do is we could split this up into these first pieces plus the second pieces. Okay. Next, I could pull out the scalars C and D. Do you see that it helps that I kind of know what I want this to equal? That I want this to equal the right-hand side of property 4. So we kind of know the direction we're headed in. Oh, did I write a... No, this looks good. This looks good. That's a V, and that's a V. Looks good. Sometimes V's and U's can look a little bit alike if you don't make the V's sharp enough. This looks good, though. So, you ready for the final trick? U2, U1. U2, U1 is equal to T of U. V2, V1 is equal to T of V. And we do get the right-hand side. That's pretty cool, right? Because I saw U2, U1, and I said, wait a second, U2, U1 is just a flipped version of U. That's what T does. T flips the coordinates. V2, V1 is a flipped version of V. So it's the image of v under the action of t. So let's write a sentence to wrap this up. So t is a linear transformation. So this was basically a proof. This was basically, I mean, you could say that we were going through this process, and over the course of doing it, we basically verified that property 4 is satisfied. If you go through this process and you like hit a dead end somewhere, then maybe you might start to suspect that property 4 is not going to be satisfied, and maybe it's not a linear transformation. And that would also be useful to know. That would also be an answer. So take a quick look before I move the page. I'm going to ask you to do one next. You can use this kind of strategy. All right, so what I'm going to ask you to try is t from example 2 linear? So I'll remind you what the transformation was. Okay, so it was t goes from R3 to R2, defined by t of x1, x2, x3, and it equals a vector with only 2 entries, x1, x2 plus x3. So I'd like you to pause the video and try to do this one. You know, justify your answer also. Okay, I'm ready to talk about this one. So it feels like we start writing this kind of in the format of a proof, and you know, we're kind of proving whether or not it is linear. Okay. I actually don't know yet which one we're proving, so we just start and see what happens. Let's let u and v be elements of the domain R3 such that u equals u1, u2, u3. V is going to be v1, v2, v3, so that when I use those letters later, we know what they mean. And let's let C and D be elements of R, because I am going to check for property 4. And I'm not going to write as many sentences as last time, but we're checking for property 4. All right, then. Sometimes I say we have. I'm using the word then. T of CU plus DV. That is the left-hand side of property 4. Ultimately, we're going to figure out, does it equal the right-hand side of property 4? I know that this is equal to T of, I think I'm going to write a little bit less this time. Let's go to this being CU1, CU2, CU3 plus DV1, DV2, DV3. When you write these, make sure that you like U1, U2, U3, V1, V2, V3, those should not have vector symbols above them, right? Because those are just entries within the vectors U and V. Okay, so from here, I'm going to do kind of what we did last time, which is I'm going to add those up to one single vector. CU1 plus DV1 is my first entry. CU2 plus DV2 is my next entry. CU3 plus DV3 is my third entry. Now I think it's time to apply the transformation t and see what kind of output we get. This transformation goes from R3 to R2. What I'm about to get is a vector with only 2 entries in it. I might draw it looking like pretty wide, like it's going to look like a rectangle, but really it's just a column vector. It has to be kind of wide to fit what's going to go in there. So let's get started. First entry. So this transformation, what does it do? It takes the first entry and just puts it there as the first entry. That's the easy one. First entry goes to first entry. Let's do that. First entry of our input is the first entry of our output. Okay? It's the second entry of the image that we need to think about. That's x2 plus x3. It's not that bad, though. All this says is take entry 2 and entry 3 and add them together. So entry 2 and entry 3, I'm going to add them together. So cu2 plus dv2 plus cu3 plus dv3. That's not bad. We did it. So let me tell you what I have in mind here. I'm thinking about what property 4 looks like. I'm hoping that this will all equal like the right-hand side of property 4. If it's going to work, if it's going to equal the right-hand side of property 4, the right-hand side of property 4 has a c t of u plus d t of v. So c t of something plus d t of something. So I feel like I want to take the parts that involve c and kind of separate them, and the parts that involve d and separate them. So what I'm going to do is pull out c of some of it and pull out d of the rest. What do you think of that? Because I know where we're headed. I know that we're trying to make this look like the right-hand side of property 4. I'm not assuming property 4, but I'm trying to make it look, I'm trying to get there. If I pull c out of the, let's just focus on the first entry. If I pull c out of this, I get a u1. And when I pull d out, I get the v1. That seems good. Second entry, if I pull c out, what am I pulling c out of? cu2, cu3. So we have u2, u3. If I pull d out front, what am I pulling d from? I'm pulling it from dv2, dv3. So v2 plus v3. You can check that these two things are equal to each other. But I like what we got here because it looks closer to the right-hand side of property 4. Now, did we get where we wanted? Did this work? Did this work out perfectly? Look at this. What is this thing? Doesn't this look like t of u? Yeah, if you put u in to t, this is what you get. What about this? If you put v in to t, this is what you get. So look what we got. We got c t of u plus d t of v. That's exactly what we wanted. We got there by trying to get it into that form. And, you know, you can't force it if it's not going to equal it. Like, if it doesn't equal it, then you can't make it equal it. But in this case, we tried to get it in that form, and then we got here and we checked, and yes, it did work out. So t is a linear transformation. So far, we've seen 2 linear transformations. The first one was the one, example 1 up above. That's linear transformation that swaps x and y. And this is a linear transformation that does something a little bit different. So this shows us that you can have a linear transformation from R3 to R2. They don't have to be the same size vectors. So I bet you know what's coming next. Example 3 from earlier. Again, I'm going to ask you to try this, but I'll get it started for us. I'll write the transformation. Is t from example 3 earlier linear? And this was t from R2 to R, defined by a formula. T of x1, x2 equals the product x1 times x2. All right, so I'd like you to pause, take a couple of minutes, and see what you can find for this one. Okay, so again, I'm going to be checking for property 4. Let's make a little dividing line here. Let's move this page up. Let's start with the usual thing of establishing, U and V and C and D. Because the problem doesn't mention a U, a V, a C, or a D. So if we're going to use them, we should establish what they are. U and V are going to come from R2. Okay, they're coming from the domain. So we'll say such that U is U1, U2. V is V1, V2. And let C and D be elements of R. We want scalars. We have. Let's start with the left-hand side of property 4, which we're going to be checking. If property 4 is satisfied, then this will be a linear transformation. If property 4 is not satisfied, well, we'll talk about that when we get there. T of Cu plus dV. Following kind of what we did last time with the other ones, we would say Cu1, Cu2. Seems like a lot of these start off the same, right? CV1, CV2. Sorry, these should be Ds. dV1, dV2. Okay, that looks good the way it is. And this equals T of, we try to get this to be just a single vector. So Cu1 plus dV1, Cu2 plus dV2. Okay. That's about as far as we can go doing that. The next step is now let's actually apply the transformation T to this vector. So we have T of a vector. Up above, we have the rule for what it's supposed to do. It's supposed to take the first entry and the second entry and multiply them together to get us, in this case, first entry times the second entry. That's my output. Okay. We want this to equal the right-hand side of property 4 if we're going to show that this thing is linear. Now, let's think about what the previous problems looked like. Previous problems, we found a way to like pull out C, pull out D, and kind of have C times something plus D times something. Can we do that here? Let's try to work with this. I guess we could expand. Let's kind of distribute, right? So first term times the next term, Cu1 times Cu2 is C squared U1 U2. Let's do the outer terms. CD U1 V2. Inner terms, CD. Which order do you want to write them in? Let's write the U's first. U2 V1. And then finally, D squared V1 V2. I don't like that C squared, and I don't like that D squared. can we make this equal C? I guess we would want this to be C times something plus D times something. This does not look like it's going to work out, okay? I feel like at this point, maybe even in the previous step, once we got to here and I saw this multiplication happening, at this point, it looks like the answer is probably no. We haven't proved it yet. Right now, we can't say because of this work, example 3 is not a linear transformation. We haven't proved that yet. We haven't proved it one way or the other. But I got to this point and I am strongly suspecting that it is not a linear transformation because I don't think that this is going to equal the right-hand side of property 4. So what should we do? What should we do to prove that this is not a linear transformation? We're not actually going to be able to prove property 4 if that's the case. Let's write some of this. What should we do? I am suspecting that property 4 is false. Property 4 does not hold for this. So how can we show, to show t is not linear? If we were in class right now, I would ask, does anyone have any ideas? Since this is pre-recorded, I guess I have to tell you, don't I? To show that this transformation is not linear, how about we demonstrate a counterexample to one of the properties. And I'm going to underline the word counterexample. You learned about counterexamples when you learned about how to write proofs. We're trying to show that something is not true. Counterexample would be a good way to go. So maybe we could find a counterexample to property 1. That would be enough. That would be enough. Or counterexample to property 2. Or counterexample to property 4. You know what else? Don't forget about property 3. Property 3 is something that holds for all linear transformations. So if you could find a counterexample to property 3, that would actually be like really convenient and really quick. But I'm looking for it. It's t of the 0 vector equals the 0 vector. Like if you ever wanted to find a quick counterexample, check that one. Do we have that here? Well, it looks like in this case, t of the 0 vector does equal the 0 vector. So it looks like this does satisfy property 3. So I'm going to say that that's kind of unfortunate because I was hoping to get a quick counterexample out of this. Like if t of 0 equaled something else. How about we look for a counterexample for property 4? Because that's the property that we've been working with the most. We need a u, we need a v, we need a c, and we need a d. So how do we choose these? Like, how do we know what to pick? We're checking to see, we're trying to show a counterexample to property 4. Here's what I'm thinking. This thing, when we tried to show property 4 was true, we got to this thing, which is a total mess. It looks like it's very different from property 4 from the right-hand side. What's going to happen here is that almost any choice will work. If t is not linear, then almost any choice will work. So I'm going to choose a vector 1, 4, a vector 2, 3, c is 1, d is 2. Don't choose like something that seems too trivial. Just pick some numbers like this. The reason why I'm saying that almost any choice will work is because if t is not linear, as we strongly suspect right now, it would be a very big coincidence for property 4 to somehow be satisfied for this given choice. We chose U, V, C, and D. Wouldn't it be a really big coincidence if it all worked out and property 4 was satisfied? So anyway, let's try property 4. Let's see the left-hand side of it. CU plus DV. This is a counterexample, so I'm trying to show that the left-hand side of property 4 does not equal the right-hand side of property 4. So this is 1, 4 plus 2, 2, 3 equals T of 1 plus 2 times 2 is 5. 4 plus 2 times 3 is 10. Apply the transformation and we get 50. So the left-hand side of property 4 is 50. Let's check the right-hand side of property 4. I suspect we're going to get something that's not 50, and that this will be a counterexample. So T of 1, 4 plus 2 T of 2, 3 T of 1, 4. Let's remember what this transformation does. It multiplies those. So that gets me 4. 2 times T of 2, 3. That's 2 times 3 is 6. So this is 2, 6. The vector 4 plus 2 times the vector 6. This gets me 16. And this are not equal. So we found a counterexample. So property 4 is not satisfied. Property 4 is supposed to be satisfied for all U and all V and all C and all D, but we found a U, a V, a C, and a D that makes property 4 not satisfied. So we can definitively say T is not a linear transformation. It is still a transformation, but it is not a linear transformation. So let's just quickly review what we did on this one, okay? Because this took up a full page. The ones where it did work out, the ones where it was a linear transformation, those seemed a little bit more straightforward. We knew like where we were starting from. We knew where we wanted to end up. Everything worked out beautifully. On this one, I started by trying to check to see if property 4 was satisfied. I got about halfway through the process and I said, this doesn't look good. This looks like a mess. Like it's probably not going to equal what I want it to equal. So we took a step back and we said, you know what? I think T is not linear. How do we show that it's not linear? Counterexample. Let's just try some kind of U, V, C, and D to see if we can confirm our suspicion that it's not linear. I checked the left-hand side of property 4. I checked the right-hand side of property 4, and I did not get the same thing. So property 4 is not satisfied, so T is not a linear transformation. Even though I think that this transformation does satisfy property 3, it's still not a linear transformation. Okay, so got a little more to talk about. By now, I think that you should be good if I give you a transformation with a formula and I ask you, is it a linear transformation? I think that you should be able to check. Either by checking property 4, as we've been doing, or the other alternative is you could check properties 1 and 2. I mean, that means you have to check 2 things instead of 1 thing, but the 2 things that you check are a little bit simpler. So it's up to you. All right, a fact. Let A be any m by n matrix, then T from Rn to Rm defined by T of x equals Ax is a linear transformation. Okay. Take a rectangular matrix, could be a square. You set up the mapping to go from the appropriate sized Rn to the appropriate sized Rm to make sure that it matches up with the size of the matrix, m by n. T of x equals Ax is a linear transformation. That's actually a pretty cool fact because that gives us like an entire big family of linear transformations. Like any matrix that you can think of. It says any matrix. So pick any matrix that you could think of. There is a linear transformation if you set it up to be Ax. That's pretty cool. Why is this true? Do we need to go through like all that work of like checking property 4? Is it going to take a really long time? No, I could actually show you why very quickly. And it's because earlier in a previous video, we had something called Theorem 5. Let me see which lesson was this. This was Theorem 5 from the lesson on the matrix equation. I guess I could have just said from a previous lesson. I could have just left it at that. All right, but anyway, it was from that lesson. It says that when you have a matrix times a vector plus a vector, it equals AU plus AV. That was a property of matrix times vector multiplication. And that same theorem also said ACU equals CAU. Pretty cool. So properties 1 and 2 are satisfied. Pretty cool. So it follows from these properties of matrix multiplication that the two conditions of being linear are satisfied when you define a transformation in this way. Now, I'm going to tell you a quick little terminology thing, quick little notation thing, I guess. We sometimes refer to this transformation, because it comes up so often, these types of transformations, as the vector x, and then we use an arrow pointing to the right, but with an extra little mark, a different looking arrow. Take a look at that. AX. X with an arrow pointing to the right, AX. But the arrow looks a little different. And the way that this should be interpreted is it's like saying we're talking about the transformation that maps the vector x to the vector ax, because ax does get you some vector, some kind of output vector. So I've got a problem for you to try, but it's not going to be another one of those, is it a linear transformation? Got something else instead. Just something about one of these AX linear transformations. So how about I'm going to give you T from R2 to R3 defined by T of X equals AX, where A is going to be given as this matrix 1, 0, 0, 3, 1, 2. So that's given to us. And I'm going to have two questions. Before I even ask you the questions, I just want to acknowledge one thing. We already know this is a linear transformation. You don't have to check property 4. You don't have to check property 1 or 2 or 3. We know it's linear because of what we just said above. Pretty cool that we automatically have this as a linear transformation. That actually means that we know properties 1, 2, 3, and 4 hold. Those properties are satisfied. If we wanted to use them to help us do something, we could use them. All right, I'm going to ask you two parts. First part, pretty simple. Given u equals -1, 1, I'm going to ask you to find T of u. But wait just a moment, because I said there's going to be two parts to this. Second part is a little bit trickier. Given b equals the vector 4, 12, 12, is b in the range of t? If so, find a vector x whose image is b. If not, explain why. So that's a two-part question. So we have not done a question like that before, but you have everything you need to solve this. You have everything you need to be able to do this. So I'd like you to pause the video and spend a few minutes on this, and then check back with me and we'll go over it. Okay, so we're working with a linear transformation defined by T of X equals AX, and we were given the matrix A. That's important. By the way, I could point out that this matrix A is 3 by 2, and this transformation goes from R2 to R3, and that's good. That means like all the sizes match up the way they're supposed to. Okay. Part A. Let's get going on part A. So it wants us to find T of u. T of u is supposed to be the matrix A times the vector u. Can we do this? Yeah, we can do this. We had a section earlier on how to do a matrix times a vector. You take the first entry of the vector times the first column of the matrix, plus the next entry of the vector times the next column of the matrix. It does look like this is going to equal some kind of vector. -1 plus 0, 0 plus 3, -1 plus 2. Ultimately, what do we get here? -1, 3, 1. That's my answer to part A. That's the only answer to part A. Okay, and I could give you a different vector to put in also. I mean, this was just, here's a vector, put it in, see what you get. I could also give you like some other vector, put it in, see what you get. So that's one type of problem. Part B, though. Part B. That seems tricky. It gave us something that is not supposed to be an input for the transformation. It gave us something that's supposed to be an output. Given B, is B in the range of T? I'm going to tell you that if you think about it, this really means, is AX equals B consistent? Do you remember what consistent means? Consistent is a word that we probably used on like the very first video lesson. It basically means, does this equation have a solution? Is there a vector x that will make this work? And now, looking back at this problem, I see that the problem says, if so, find a vector x whose image is B. So yeah, we do want to find x. We want to see if there's an x that makes this work. How would we solve this, ax equals b? Well, we understand at this point in the course that ax equals b corresponds to a linear system. We could solve it with an augmented matrix. So that's what I'm going to do. I'm going to write up the augmented matrix, where the right-hand side is this thing B, and try to solve this system. When we try to solve this, we're going to be trying to solve for this vector x. And really the question is, are we going to find a vector x or are we not going to find a vector x? Is there a solution or not? So let's do row reduction. I decided to add negative r1 to r3. And I also decided to multiply R2 by 1/3. And I did both of those at the same time because those steps don't affect each other. So R1 stays the same. R2 gets multiplied by 1/3. That makes it a little bit nicer. R3 gets some stuff subtracted from it. And I get 0 to 8. Okay. One more row reduction step. You see the 1, 4 and the 2, 8? 1, 4 and 2, 8. You know, those rows, one of those rows is a multiple of the other. How about this? Add negative 2r2 to r3. Top row stays the same. Second row stays the same. Third row gets 0 gets added to 0. This gets knocked out. This gets knocked out. How about that? We row reduced, but now we're still responsible for figuring out, what does this mean? What does this tell us? I'm going to say it is consistent. There are no free variables. So there is a unique solution. Can you see when I say there's a unique solution? Can you see what the solution is? All right, let's write this up. My answer, we found that there is a solution to this. So I'm going to say yes, B is in the range of T. So that's part of the answer. It said, if so, find a vector x. We found it. It is the vector 4, 4. Then T of x will equal B. So that's my answer to this. I found the 4, 4 by looking at this, and I said, first of all, you know, what size vector x were we looking for? We know that this is a transformation from R2 to R3. So the inputs live in R2. So I knew that there would only be two entries. This would be a vector with two entries, right? I mean, if you look at part A had a vector with two entries as the input t of u. So yeah, we expected two entries. We found them because right here, the first column kind of represents the x1 column. Second column represents kind of the x2 column. And we found 1x1 equals 4, x2 equals 4. Last column doesn't tell us anything. I'm going to tell you that this step right here, you can check this if you'd like. If you'd like, similar to part A. But it's not necessary. If we were careful about everything we did here, then you don't really have to do that extra work of checking it. But what I'm saying is, we claim that putting in this input will get the output 4, 12, 12. So if you'd like, go ahead and put this into the transformation and verify that you do get 4, 12, 12 as your output. You can do that if you want. Okay, so that's the end of our lesson. This one was called Intro to Linear Transformations. So the next lesson is also going to continue talking about linear transformations. It's going to talk about them in a little bit of a different way. I'll tell you that at this point, if I gave you a transformation with a formula, I could ask you, is it a linear transformation? And you should be able to answer yes or no. You should be able to show work and justify your answer, basically proving that it is a linear transformation or proving that it is not. And then, we saw at the end there in that last problem that there's also some other types of questions that could come up as well. Something I want to say here about that last problem and kind of the last 10 minutes or so of what we did. That fact towards the end that said t of x equals ax is always a linear transformation for any matrix A. That's going to turn out to be pretty important for this course. Those are some of the linear transformations that we're going to work with the most. The ones that are a matrix times a vector. In fact, how do I say this? So we said that every time you have a matrix, that there is this corresponding linear transformation. Something I'd like you to start thinking about is, does it also work the other way around? Does every linear transformation have a matrix? See what I mean? Like every matrix has this linear transformation AX. What about other linear transformations we looked at? Example 1, example 2. Is there some matrix A that corresponds to those? Well, anyway, that's what we're going to talk about in the next video. You could start thinking about it now if you'd like, but that's kind of the question that we're going to answer. All right, so that's a good place to stop, and I hope everyone is doing well. So take care. See you for the next one.